Hello again. Now we're doing chapter 3 of this real analysis book. I make the copies myself. My name is Taha Arkian. It's based on principles of mathematical analysis. This is for chapter 3, sequences and series. Let me just see if I'm recording. Okay. So we define a convergent sequence as like this. Let Pn be a sequence in a metric space X. We say that Pn converges if there exists a point P in X such that for all epsilon greater than 0 there exists n in n, such that n greater than or equal to n implies that the distance between Pn and P is less than epsilon. And what this means is that basically you can choose any region epsilon as small as possible, and for each region you can fit infinitely many n's starting from one point n to another, such that their distance is less than this epsilon. So you can find infinitely many points lying in this neighborhood that is a neighborhood of this limit point, basically. So that's what a convergent sequence is. And we write it like this, something that's n goes to infinity, Pn equals P, or Pn goes to P. And if it doesn't exist, we say it diverges. And notice, some sequences may converge in one metric space, but not in another. So, for example, the sequence 1 over n converges to 0 in R, but doesn't converge in the space of positive real numbers. Because 0 is in R, but it's not in R positive, because 0 is not a positive number. Sometimes to get rid of this ambiguity, we say it converges in X. And the sequence is said to be bounded if its range is a bounded set. The range of the sequence is basically the set of all the values of that sequence. Now we have a few examples here. If you have s of n equals 1 over n, limit it as n goes to infinity of s of n equals 0, because 1 over 1, 1 over 2, 1 over 3, etc., this goes to 0. This sequence is convergent and has an infinite range because there are infinite amount of values. S of n equals n squared. This sequence is divergent, unbounded, and has infinite range, because n squared, when you keep on squaring and squaring and squaring, there's no limit. It goes up to infinity. So it is divergent. It doesn't converge to a single point. It is unbounded because it's diverging. It's not going to values for it to be bounded. And it has an infinite range because there are an infinite amount of values that you're squaring, and you're getting different values each time, right? And we have 1 plus negative 1 to the n over n. This sequence converges to 1, is bounded, and has infinite range. Because this part goes to 0, so we're just left with 1. It's bounded because each time this negative 1 over n is going to be smaller and smaller and smaller, so you can take a maximum and a minimum value. S of n equals I to the n, I being the complex number, which is the square root of negative 1. The sequence is divergent, bounded, and has infinite range. Because it's divergent because it keeps alternating between values. When you square I, it's going to give you negative 1. And then when you do I cube, it's going to give you negative I. And then it's basically 90 degrees rotation, right? Yeah, multiplying by I is a 90 degree rotation in the complex space. So it's going to be keep rotating, and you can't make it bound. It is bounded, right? But you can't say after some point onwards it's going to stay right here. That's what we want to have for a limit, right? It doesn't work like that. So it's divergent. It is bounded because it's basically the value of 1, but you're just rotating it. And it has finite range because it's just the values of 1 in different angles, right? So there's 4 different possibilities. S of n equals 1 for all n. This sequence converges to 1, obviously. It is bounded and has finite range. Now we have the following theorem. Let Pn be a sequence in a metric space X. Pn converges to P and X if and only if every neighborhood of P contains all but finally many elements of Pn. If Pn converges to both P and P prime, then P equals P prime. If the set Pn converges, then the sequence is bounded. And if E and X and P is a limit point of E, then there exists Pn in E such that limit as n goes to infinity of Pn equals P. Which is really nice because now we're relating the limit point to the limit itself, right? So we're kind of seeing why it's called the limit point, because it's related to the limit. Okay. Now for the proof, suppose P of n goes to P. We'll explain the strategies later because I think it's really important to see the strategies of how you're proving it. Just to have like a visual proof. I'm going to explain it in simpler words later. I'm just going to read the proof now. I'm going to keep doing this throughout the video so it's easier. Suppose Pn goes to P and let V be a neighborhood of P. Then there exists epsilon greater than 0 such that the open ball B P epsilon is in V. Because P of n converges to P, right? We're taking a neighborhood of P. And now we're taking an open ball which is in that neighborhood because we can set epsilon to be smaller and smaller, so it's contained in that neighborhood because the neighborhood itself is an open set, kind of like if you want to look at it in R2, it's kind of like an open circle, and this open ball is inside that open circle, and you can just bring it to any other sort of space, right? So we're taking this inside this set neighborhood V. By the definition of convergence, there exists n such that for all n greater than or equal to n, distance P of n, P is less than epsilon. Hence, Pn is in V for all n greater than n. Because P and P is less than epsilon, so that means it's contained inside this open ball, right? Which is in V. So that means Pn is in V for all n greater than or equal to n. So the strategy here is very basic. So you're taking the limits definition and you're also taking the neighborhood or the open ball definition and you're relating them to each other because for the limit, the absolute value is less than epsilon and you can take that to be like some sort of open ball. And conversely, you're just backtracking, doing the same kind of logic. Conversely, suppose every neighborhood of P contains all but finally many points of Pn. Fix epsilon greater than 0 and let V equals ball P epsilon. By our assumption, there exists n such that Pn is in V for all n greater than or equal to n such that the distance Pn P is less than epsilon for all n greater than n. Therefore, Pn goes to P. And here said it contains all but we want to prove that it contains all but finally many elements of Pn, and we've done that because we said that for n greater than or equal to n, all of the Pn are in V. So that means before n we have finally many points that are not in that neighborhood, right? So we can say that it contains all but finally many elements of Pn. Now for B, when we want to prove B, the strategy here is that you have 2 points converging, being the convergence of a sequence. What the trick is, you want to take them as epsilon over 2 and adding them together, right? Because you can add these sequences together to see how they work, and you can just take them to be less than epsilon over 2 to add them together to make it to become epsilon. And that's what we're doing here. Basically, since Pn converges to both P and P prime, there exists integers n and prime such that n greater than n equals this, is equivalent to this and this, so it's less than epsilon over 2. And we take n to be greater than maximum of these 2 numbers, and now we can use the metric space formula, the triangle inequality over here, and add the epsilons over 2 together to get epsilon. And notice we can take it to be epsilon over 2 because if it's epsilon greater than 0, then epsilon over 2 is also greater than 0. So we're taking all the possible values greater than 0 still by taking epsilon over 2. Suppose Pn goes to P, this is for C, right? If Pn converges and the sequence is bounded. Then there exists an integer n such that n greater than n implies distance Pn to P is less than 1. Because it converges to P, so we can limit the distance between Pn and P, and we just take it to be 1, right? We take this limit to be 1, and we take R to be the maximum of one distance between P1 to P, P2 to P, etc., to Pn to P. And we know the distance of Pn to P for all n greater than n is less than or equal to R. Because at each point, so we said that the distance between Pn to P is less than 1. And this is all the distances to limiting distances from P1 to Pn n capital, and including this limiting distance 1, right? So if Pn P is less than 1, then the n's going afterwards are also going to be less than 1. And yeah, so exactly, we have distance of Pn to P is less than or equal to R being a real number, right? So Pn is bounded. This is the definition of it being bounded. Suppose E is a subset of X and P is a limit point of E, then for each n and n there exists Pn and E such that distance of Pn to P is less than 1 over n. Because here instead of epsilon we're just taking 1 over n because we want to use epsilon elsewhere. So we're finding something to limit it that's going to get closer and closer to 0, which is 1 over n. And what we're trying to prove here is that there exists a sequence Pn in E such that limit as n goes to infinity of Pn goes to P. We choose n epsilon greater than 0, or in other words, greater than 1, or in other words, 1 over n is less than epsilon. So that means for all n over n greater than n, we have we're going to replace this 1 over n with 1 over epsilon. We're going to have distance Pn to P is less than epsilon, so we prove that Pn goes to P. Now we have the following properties. The sum of limits is the same thing as the sum of the limits separately. Multiplying by constants doesn't change, or adding by constants doesn't change. SNTN gives you ST, and the limit of 1 over Sn is just 1 over S. Now for the proof of them is the same thing. Just take epsilon over 2, add them together with the triangle inequality, and you're going to prove that their sum is the same thing. Here the trick is you want to factorize it like this and then add these terms. And notice these terms over here are basically the limits of them separately over here. It's basically these limits, right? And yeah. So we're going to take them to be less than the square root of epsilon so that we can multiply these together. And we're going to get this. But these things, if you've noticed, these go to 0 because because you're taking you're subtracting on both sides, right? So these things go to 0. So this expression eventually just becomes this expression, and you're taking these to be square root of epsilon. So the strategy is you're taking a bigger expression so you can reduce it, and you're taking the multiplication of it, so you take square root of epsilon so that you can multiply them together, right? So that's for the proof. And if you want to prove that the limit as 1 over Sn goes to 1 over S, basically we take Sn minus S is less than 1/2 S, which means by the reverse triangle inequality we get Sn is greater than 1/2 S, and you can just multiply it again to get Sn minus S is less than you can choose it to be this, so that it's neatly simplifies here when you do the subtraction and gives you less than epsilon. That's the strategy. And for point-wise convergence in RK, basically component-wise convergence in RK, The sequence xn converges to x equals x1, x2 to xk in Rk if and only if for each j equals 1 to k, limit as n goes to infinity of alpha jn equals xj. So basically each dimension is converging separately. So basically in Rk, if you want it to converge, which means basically the norm of it is converging to something, you want it to converge separately in every dimension. And this follows because the norm of this is always greater than this, because this is basically, this is one of the components of the norm squared, right? If you take the square root on both, if you take the square root, definition of the norm is square root of one component squared plus the other component squared, etc. This is one of the components, and it's inside the other ones, right? So it's going to be less than or equal to that. That's the strategy over here. And conversely, if you want to prove that if this if it converges like this, each component converges like this, you can take it to be less than epsilon over root k, such that you can take it to be inside these terms for the norm, and you square them to get to the normal k, and you do it k times so that k is cancelled. So that's the strategy. You want the k's to cancel, and you take the square root and you get it to be less than epsilon, which is what we wanted. And what follows is that even the sequences, when you multiply them, add them, or multiply them by the constant in the Rk, you get the same thing for the limit. Now we have a subsequence. A subsequence basically means you're taking a strictly increasing sequence of positive integers, and you're taking the sequence of those you're indexing those integers. You're taking those integers as indexes of this sequence. So if you have the integers to be 2, 5, 7, etc., you're taking the second term, the fifth term, the seventh term, etc. That's the subsequence. Now we have the following theorem. Let Pn be a sequence in compact metric space X, then some subsequence of Pn converges to a point of X. Every point, and the second theorem is that every point sequence, bounded sequence in Rk has a convergent subsequence. So basically we have two cases here. We want to examine them equally. One case is that we have a finite range, and the other case is that we have an infinite range, and we want to see them separately. If E is finite, then some point P in E appears infinitely often in the sequence, because the sequence is infinite. You're having finite points, so of course you can't you don't have infinitely many points to fill in these infinitely many places. So you're going to have to repeat these finite points. In that case, we can extract a constant subsequence P and K with P and K equals P for all K, which clearly converges to P. So the strategy is to take a constant subsequence, which we know will definitely converge. If E is infinite, then by theorem 2.37, the set E has a limit point P in X. We now construct a subsequence converging to P. So this limit point P, we can take any neighborhood with it, right? Because it's a limit point. So P to Pn, this is from P to Pn minus to Pn1. We choose it to be less than 1, and then after that we choose n1, n2, nk, etc. to find nk is greater than nk minus 1, and we're going to choose the distance of Pn to Pnk is less than 1 over k. Then Pnk is a subsequence of Pn, and Pnk goes to P. Let me just take a look in the book real quick to give you a more exact idea of this proof, because I'm not sure if we're using theorem 2.20 here, and we just want to make sure what that theorem is. Yes, okay, so it's a theorem that every neighborhood of P contains infinitely many points of E. Yes. Basically, we're just taking this like to be like some sort of epsilon over here, and we know the smaller and smaller we get for this limit point, we can still find points p and k in it because it is a limit point. So that means it converges with some subsequence, right? Because okay, I know how to explain this. Because you might have a sequence that doesn't necessarily converge, right? So P1 might be here, P2, P3, and it becomes bigger and bigger, and you can't reach them. But you can still find other points other than the ones that diverge that are in this neighborhood, because the definition of a limit point is that you can always find points in that neighborhood. So it doesn't matter which index it is, because some indexes will diverge. You're taking the neighborhood and you're going to definitely find some indexes that converge, and you're taking it to be less than this distance 1 over k, and as it goes to infinity, we can find arbitrary many values epsilon greater than 0, and we can say that it converges for the subsequence. And B here follows from the Hein-Borel theorem, because if it's a bounded sequence and it's closed, it's going to be compact, and we're just using the same theorem over here. Now, you have the following theorem. Let Pn be a sequence in a metric space X, then the set of all subsequential limits of Pn is closed in X. So, set of all subsequential limits is that you take all the subsequences and you see which you take the limits, and you're going to see to which points they converge. Now for the proof, let E star be the set of all subsequent limits of Pn. Basically what we want to prove is that if Q is a limit point of E, we must show that Q is in E. And the strategy here is that Q is a limit point of E, so it contains infinitely many neighborhoods that contains a point Pn, right? And you can take the distance between that and Q to be less than some distance epsilon, and you can choose other points. Basically, okay, let's read the proof and then I'll try to explain the strategy later. Choose n1 such that Pn1 is not equal to Q. If no such n1 exists, then Pn equals Q eventually, and Q is trivially a subsequential limit, obviously. Let delta equals distance between Q, P, and I. So we're choosing some subsequence, right? It's Pn1, and the distance is greater than 0. Choose Q. Since Q is a limit point of E, for each I in N, we can find a limit point. We can find a point X in E such that the distance between X to Q is less than 2 to the negative I delta. For each xi being a subsequent limit, there exists ni greater than n minus 1 such that the distance between P and xi is less than 2 to the negative I delta. So the purpose of this 2 to the negative I here is that once we take it to go to infinity, it's gonna go to 0, and we've proved our point that we can take any arbitrary values greater than 0 to limit this neighborhood. And I think you can just take any values. You don't really necessarily need to take 2 here. You can take 3, 4, etc. Right? And basically you're taking the distance between that limit point and some points in that set, and then taking the distance between all the PNs and the other points in that set E, because we know okay, suppose we have a sequence, a point it converges to, and then the limit point, right? The distance between the sequence and the limit point is always contained to be arbitrarily greater than 0, and the distance between the limit point and another point is always contained to be arbitrarily something greater than 0. Any number that's greater than 0, like doesn't matter how small it is. So basically both are limited, and you can just add them together and get the triangle inequality, right? And we're going to get this, and as I goes to infinity, distance p and q goes to 0, so p and I goes to q. Thus, q is a subsequential limit of pn, so q is in E. Now we have the definition of a Cauchy sequence. A Cauchy sequence is the same thing, but now we're taking the distance between pn and pm less than epsilon. So I like to view a Cauchy sequence as maximum pressure on a sequence, because the definition of a sequence is, when it converges, is that you're taking one fixed point and the sequence itself. So you're just letting this sequence approach this point, right? But when you take a Cauchy sequence, you're taking the sequence and the sequence itself for any arbitrary points, no matter how bigger they are, right? So you can take this point and this point, this point and this point, this point and this point, etc., all the way to the end. So you're putting maximum pressure on the sequence. And the interesting part that we'll see later is that a Cauchy sequence converges, and every convergence sequence in RK and some other metric spaces are Cauchy sequences. So we define the diameter of a set to be the supremum of the distance of P and Q for every P and Q in E. And when you have a Cauchy sequence, by the definition of a Cauchy sequence, the limit as n goes to infinity of the diameter of En, when you set En to be equal to the sequence, starting the sequence at n greater than n, so at n plus 1, n plus 2, n plus 3, etc., that diameter will go to 0, because we're taking the distance between Pn and Pm to be less than epsilon, and basically here we're taking the sets Pn greater than n, so we know that for any points in that set, when it goes to infinity, is going to be less than some arbitrary epsilon that's very small. So for every point in that, if you take the biggest difference, it's always going to go to 0, because that's the definition of a Cauchy sequence. Theorem 3.10. If E is the closure of a set E in X in a metric space X, then diameter of E closed, the closure is equal to diameter of E. And we have the following theorem: let Kn be a decreasing sequence of compact subset X. So K3 is in K2 is in K1, etc. And suppose that the limit as n goes to infinity of diameter of Kn is equal to 0. Then the infinite intersection of Kn consists of exactly one point. So the proof here is that we want to see some inequalities and prove that these inequalities are going to be the same thing, so it's equal. And one way is that we take E is inside E closure, so we take the diameter to be less than or equal to it. The other way is that you're going to say, okay, we have some limit points, epsilon, sure, less than epsilon, sure, let's add them together. It's still going to be the diameter of E plus some sort of epsilon expression. And we know that epsilon expression goes to 0, so anyway, we're just going to be left with the same thing, which is basically what we're doing here. We choose PQ in the E closure. There exists P prime Q prime in E such that P prime less than epsilon, distance P to P prime is less than epsilon, distance Q to Q prime is less than epsilon. So the distance from P to Q is less than or equal to the triangle inequality over here. Is going to be less than 2 epsilon plus diameter of E, and since epsilon is arbitrary, we get this. So, and when we combine it with this, this expression over here, we're going to get diameter of E equals diameter of E closure. Now, for the second proof, let K equals the infinite intersection of Kn by theorem 2.36. The intersection of nested non-empty compact sets is non-empty. That's what we saw in chapter 2, right? So K is not empty. Suppose K contains at least two distinct points, then diameter of K is greater than 0 since K is in Kn. So if it contains two distinct points and that are different, right? So the diameter is obviously going to be greater than 0. So that means all the diameters of the Kn are going to be greater than 0 because each K is in Kn. So that means diameter of Kn doesn't go to 0, which is against our hypothesis. So it must contain exactly one point. In any metric space X, every convergent sequence is a Cauchy sequence. This is what I was talking about earlier. If X is a compact metric space and if Pn is a Cauchy sequence in X, then the set Pn converges to some point in X. Every Cauchy sequence in Rk converges. Okay. Suppose Pn converges to P in X, let epsilon greater than 0 be given, then there exists n such that for all n greater than or equal to n we have the distance of Pn to P is less than epsilon over 2. So we know the distance between Pm to P, now if you take M here to be here, is also going to be less than epsilon over 2. So the strategy is taking the sequence with itself 2 times, setting them to epsilon over 2 so that you can add them nicely to become epsilon and show that this is the Cauchy criterion. Okay, so if X is compact, so we read this theorem, we want to prove it now. Let Pn be a Cauchy sequence in the compact metric space X. Define the tails of the sequence En equals Pn n greater than n. By theorem 3.10 we have limit as n goes to infinity of diameter of En equals 0, that because that's what we just proved right now. Each En is closed subset of compact set X. Moreover, so we know the intersection has exactly one point. For epsilon greater than 0, choose n naught such that diameter of En is less than or equal to epsilon for all n greater than naught. Because we know the limit goes to 0, so we can take this this statement over here. Since P is an En, we have distance of P to Pn is less than epsilon for all n greater than n naught. Because this is less than the diameter, less than or equal to the diameter, because P is an En, and we know that Pn is a limit point of that sequence. So we can take them both to be in that En. So it's going to be less than the diameter of En, less than epsilon. Hence, Pn goes to P. This is what we wanted to prove, that if it's a Cauchy sequence, then it converges to some point in X. Okay, so now we want to prove every Cauchy sequence converges in Rk. Let Xn be a Cauchy sequence in Rk. Define En as in B. Since Xn is Cauchy, there exists n such that diameter of En is less than 1. The range of the sequence is contained in En union x1 which is bounded. Okay, so we know the diameter of En is less than 1 for some point onwards. So we know that from some point onwards it's bounded. And we know that every finite set of points is bounded. So union of bounded sets together is bounded. So every bounded subset of Rk has compact closure. So Xn lies in compact subset of Rk and B applies. And we get the third property, that every Cauchy sequence in Rk converges. Now, complete metric spaces. We have a metric space X is said to be complete if every Cauchy sequence in X converges to a point in X. Now, an example of a metric space that is not complete is a set of rational numbers. So you can take the sequence of approximately root 2, so the first digit of root 2 and then the second digit of root 2, etc., etc. So you have 1, 1.1, 1.4, 1.41, 1.414, etc., etc. And this converges to root 2, which is not in Q. So it doesn't converge in Q, so that means it's not complete. It's not a Cauchy sequence in Q. So that's an important example of a metric space that is not complete. Now we have monotonic sequence and convergence. We say that it's monotonically increasing if every number is less than or equal to the next number, and monotonically decreasing if s of n is greater than or equal to s of n plus 1. So it's basically increasing or decreasing, and we're setting a limit point for each level. So if it goes from here to here, if it decreases, then it can't increase anymore. It's either going to stay the same or go down. That's what we're saying. Now, so we want to prove that it's the same thing to say s of n converges and s of n is bounded when you have a monotonic sequence. We already know that if s of n is bounded, then s of n converges. We want to prove that if s of n converges, then s of n is bounded right now, right? So assume s of n is monotonically increasing. Let E. The strategy here is to find a supremum, because we know it's. Actually, we want to prove that if it's bounded, then it converges. Not that, because. But sorry, I made a mistake. If it converges, then it's not. It is bounded. It's definitely bounded. But if it's bounded, doesn't mean it converges. So we want to prove that. We know that if it's monotonically increasing, then we have a least upper bound, and we want to use that as some sort of limit point, right? And show that using that limit point, we can use this property to get to the definition of a limit, because it's very similar to just taking neighborhoods to be less than or equal to something that is very small for both cases, and you're just relating them to each other. So given epsilon greater than 0, the number s minus epsilon is not an upper bound of E. So there exists an index n such that s of n is greater than s minus epsilon. Since the sequence is increasing for all n greater than n, s minus epsilon is less than or equal to sn is less than or equal to s. So we can say that it's in some sort of neighborhood, and it converges to s. Now, when we have divergence to infinity and negative infinity, basically we're finding an n greater than n such that s of n is greater than or equal to to some number m for every number. So for every number, you can every imaginable number, you can find some point of a sequence that is greater than that. So of course it's going to go to infinity, because if for every number it's going to be greater than it for some point onwards in the sequence. And basically it's the opposite for negative infinity. Now we have what we call the lim inf and the lim sup, which is the lower limit and the upper limit. And you're basically taking the set of all subsequential limits. Its infimum is going to be s star, and its supremum is going to be s star on the top. And you're taking lim inf Sn to be S star bottom and lim sup Sn to be S star up. So you're taking all the possible convergences. The maximum convergence is going to be lim sup. This minimum convergence is going to be lim inf. Okay, so we have the following theorem. Let Sn be a sequence of real numbers, and let E and S star be as in definition 3.16. Then S star is an E. If X is greater than S star, then there exists N in N such that for all N greater than N, we have S of N is less than X. So we have three cases. One is S star is plus infinity. And we really don't have anything to prove for these two cases over here, for S equals plus infinity and S equals negative infinity. Because for S equals negative infinity, that means there's no real points before it. So S of N is greater than M only infinitely often. So again, S star is an E. So let's just read the proof from the beginning. S star equals plus infinity. Then E is unbounded above. So the sequence is not bounded above. Hence there exists a subsequence SNK such that SNK goes to infinity. Therefore S star is an E. S star is an R, then E is bounded above by a theorem. Because every sequence of real numbers, every segment, right, or every interval, every segment actually contains its supremum, contains its lower upper bound, right? So that means S star is an E, and same follows as here. Now here the strategy to prove this is that if X is greater than S star, we know that you can't for every sequence that you take, its limit is going to be less than X, and since you know that from any point onwards this is going to be less than X because the maximum of it is S star. So that's the strategy here. Suppose X is greater than S star. If Sn is greater than X for infinitely many N, there exists a subsequence Snk with Snk greater than X. Okay, this is what we're assuming. We're assuming the exact opposite. And any limit point of y of the subsequence would satisfy y is greater than or equal to X is greater than S star. So that means there's a limit point greater than S star, right? So it contradicts the definition of the supremum. That's basically what I was trying to say in other words in the beginning. Therefore, for all sufficiently large N, Sn is less than X. And you can see the proof for the uniqueness here. Now we have examples. Let Sn be a sequence of all rational numbers. Then limit S sub Sn equals this is called a dense enumeration, basically. This sequence containing all rational numbers. Then every real number is a subsequential limit. You can take it to be plus infinity and negative infinity, because as you go up and up in the real numbers, you get plus infinity, and if you go down and down, you get negative infinity. So that's going to be lim sub and lim inf. Now for B, let me just check something. Yeah, okay. So we have lim inf equals -1 and lim sub equals 1. Why? Because as n goes to infinity, this goes to 0. So we're just left with -1 over -1 to the n over 1. So we're just left with -1 to the n. And you're just alternating between -1, 1, -1, 1. So if you take one subsequence, which is a lower one, you're going to get -1, -1. The upper one is going to be 1, 1, 1. So you're going to get lim inf Sn is equal to -1 and lim sub Sn equals to 1. And for any real valued sequence Sn, we have limit as n goes to infinity of Sn equals S. Implies that limit as sub of is equal to lim inf equals to S. Because if it converges, it must converge to the same thing for every subsequence, right? That's what we showed earlier. And obviously you have this the following theorem here: lim inf of Sn is less than or equal to lim inf of Tn when we have Sn is less than or equal to Tn for all n greater than n, because everything is bigger or equal. So if you take the lowest limit, you're anyways going to get the same thing. You're going to get less than or equal to, and the same thing over here. Now we proved some basic convergence of sequences. So limit as n goes to infinity of 1 over n 1 over n to the p equals 0. Limit as n goes to infinity of this is supposed to be nth root of p, not p root of n, is equal to 1. There's a mistake here. Limit as n goes to infinity of nth root of n equals 1. And if a is an r and p greater than 0, then limit as n goes to infinity of n to the alpha over 1 plus p to the n is equal to 0. And if x is the absolute value of x is less than 1, then limit as n goes to infinity of xn equals 0. So the trick here, for the first one, you want to take n greater than 1 over epsilon to the 1 over p, such that when you replace it, you're going to get that this sequence is less than epsilon, because this is basically undoing what this is doing. When you plug it in, you're going to get epsilon. So it's going to be less than epsilon, and this is what you're going to get, and that's the proof of it. So limit as n goes to infinity of 1 over np equals 0. If p greater than 0, we said xn equals root nth p root of n. Sorry, nth root of p over here. There again, this is a mistake. Nth root of p. Then 1 plus xn to the p equals n. Basically, this is what we're saying over here. And the trick here, the strategy, is that we want to use a binomial theorem to because we want to exponentiate something, right? We want to exponentiate some terms. So the trick here is to use the binomial theorem, because in the binomial theorem you're basically expanding that exponentiation, and you want to take one of the terms of that binomial theorem to be the limit point, so that you can take it to be less than or equal to that thing, right? And then setting a bound for that sequence and letting it go to infinity, you can prove the convergence. This is what we're doing. That's the strategy. So 1 plus xn to the p is basically is greater than 1 plus p xn, because that's just one of the terms of the binomial theorem, right? Because there's more to the expansion. So I think there's a mistake here again. I'm really sorry for this over here. There's actually like a lot of mistakes in this section. But anyways, yeah, there's a lot of mistakes here. Xn is supposed to be less than or equal to p minus 1 over n. So replace p with n here everywhere. Just replace p with n. Basically you're going to get that x naught is less than or equal to p minus 1 over n, and as xn goes to so xn goes to 0, right? Because as n goes to infinity, that means xn is greater than is less than or equal to 0, as also greater than or equal to 0. So it is equal to 0, right? When the limit goes to 0. And the strategy for nth root n is the same thing, but now when you have nth root n, it doesn't simply cancel out. So you want to take because it is going to be equal to n when you exponentiate to the n power, right? So when you divide on both sides, you won't have any n's to go to infinity so that it goes to 0. So you want to have a second extra term. So you're going to get n choose 2 xn squared. And you're going to get the following, and this goes to 0. Now, okay, for this is for the third one. It's for this property over here. So you're doing the same thing. What you want to do is that you want to get rid of this in some ways, or simplify it a little bit, right? So you use a binomial theorem again, but now you choose it for the kth term, and the kth term is going to be equal to n times n minus 1 dot 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 to n minus k plus 1 over k factorial times pk, p to the k, right? So, and we're choosing it for n, basically the strategy here is to choose it for n greater than 2k. If it's not written here, you gotta choose it for n greater than 2k, so that you can take all these terms to be greater than n over 2. So you can exponentiate to nk to the k, over 2 to the k. Why we're doing this is to because we're dealing with another n over n to the k over here, right? Into the alpha actually. So we want to have some sort of n to the k term. And if we want to do that, we need to set n greater than 2k. So we get this. And now doing this, we get 2 to the k factorial over p to the k times n to the alpha minus k. And we know this goes to 0 since alpha minus k is less than 0, right? Because this is going to go to negative infinity, and n to the negative infinity is just going to 1 over n to the infinity is going to go to 0, and we're going to get that this is equal to 0. And for the proof of E, just set alpha equals 0 for this section over here. So you're going to get 1 over 1 plus p to the n, and we know p is greater than 1, right? This is for p greater than 1. Sorry, for p greater than 0. So it is going to satisfy 1 over 1 plus p when p is greater than 0 is the same thing as 1 over x when when the absolute value of x is less than 1. Sorry, it's the same thing as okay. 1 over 1 plus p when p is greater than 0 is the same thing as x when the absolute value of x is less than 1. Because 1 over 1 plus p, the biggest it is 1, and it gets smaller and smaller. It's the same thing for x, right? So it's a similar proof. Now we have series. It's basically the sum from one point to another, like this. I'm pretty sure you're all very familiar with series. Otherwise, you wouldn't be doing real analysis, that's for sure. Yeah, okay. Sometimes it's written as this or this. And we can take each individual term to be the subtractions of each sums, because it's a difference every time you're adding, right? So now we have the Cauchy criterion for series. It's basically this converges if and only if this happens, right? And this basically, that means this is, if this converges, this is a Cauchy sequence. If it's a Cauchy sequence, then the sum am and the sum an, when you subtract them, you're going to get the sum from n to m, right? And this must be less than epsilon. This is a Cauchy criterion. And basically, this is the way you're going to describe convergence of series. And what the really interesting part here is that when you set m equals to n, you're going to get an is less than epsilon. What that means is that an minus 0, its absolute value is less than epsilon, which means it goes to 0. So that's a condition, a really important condition we get, that if the series an converges, then the limit as n goes to infinity of an is equal to 0. But it's not sufficient because 1 over n doesn't converge. Its series doesn't converge, but an goes to 0. So it's not really a sufficient condition for convergence. And we'll discuss this in the later section. Now, a series of non-negative terms converges if and only if its sequence of partial sums is bounded. Because sequence of partial sums is a monotonic sequence, and if it's bounded, that means it converges, because we just proved that. Now, the comparison test. Let sum an, sum cn, and sum dn be a series of real numbers, and let n not be a fixed positive integer. If the absolute of an is less than or equal to cn for all n greater than n naught, then cn converges, and if cn converges, then sum an converges, and the opposite for divergence, right? And the trick here is that the sum from one point onwards is going to always be less than that. So you're going to get the sum of this is less than the sum of this, which is less than epsilon. So you're going to get the sum of that is also less than epsilon. And you can do the opposite for divergence. It's written over here. Now, we get the following property, and this follows from this because, as you've seen, if you factorize and simplify a sum of geometric series, you're going to get this. And as n goes to infinity, and when you have x less than 1, this is going to go to 0, so you're just going to be left with 1 over 1 minus x. I'm pretty sure you've seen that in calculus. And now we have the Cauchy's condensation test. And this actually works for any number, not just 2. You can take it to be 3, 4, etc. Because we're just taking 2 for the statement, but you can do the same exact proof with other numbers by taking bigger and bigger groups. Instead of taking groups of 2 to the k, you take groups of 3 to the k, 4 to the k, etc. And I'll show you what I mean by groups here. Okay. The proof, we take these to be the partial sums of both series. Now you see we're grouping them together. If n is less than or equal to 2k, we're going to take all the numbers less than 2k for the indexes. So Sn is going to be less than or equal to this. Now you're going to group them together, right? And we know it's a sequence that is decreasing, and it's greater than 0. So you can group them together, and each time you're taking 2 to the k. So here taking 2 to the 1, 2 to the 0, 2 to the 1, 2 to the 2, which is 4, etc., etc. And you're repeating them 2 to the k times, and you know each one of them is less than the other ones. So you can take them to be like this. So Sn is less than or equal to Tk when n is less than 2 to the k. And you can do likewise when it's greater than 2 to the k. You can group them again. And here Sn is going to be greater than this. It's going to be greater than 1/2 a1 plus a2 plus 2a4. Because here we're starting a little later. A3 plus A4 is going to be 2 times, and because A4 is less than that, so it's going to be less than 2. It's going to be greater than 2A4, right? Because instead of A3, you're replacing it with A4, so it's going to be less than that, etc., etc. And so you're going to get Sn is greater than or equal to 1/2 Tk. So for any partial sum, it's always going to be this less than or equal to this, or let this greater than or equal to this. So both you can always find partial sums that are contained like this. So that means both are bounded or both are unbounded. It depends on the series. So that proves that their convergence imply each other. Now we have the p-test. So this series 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. We use the theorem over here. We take 2 to the k times 1 over 2 to the k to the p, and we're going to get this. The ratio is 2 to the 1 minus p, and this is less than 1 when p is greater than 1. We're using the property that we saw for the special limits over here. For these ones over here. This is what we're using. So you're going to get that it converges for p greater than 1 and diverges if p is less than or equal to 1. And we use the same condensation test. Like I explained, you can take any groupings. Like instead of taking groupings of 2 to the k, you can take groupings of 3 to the k, 4 to the k, etc. And you have the generalized Cauchy theorem. That's what Cauchy condensation test, basically. And we're using the Cauchy condensation test here again. It's going to give us this. And we know 1 over kp converges, and it's just 1 times 1 over log 2 to the p. And this is going to converge for p greater than 1. And it's going to diverge for p less than or equal to 1, right? And you can continue likewise with these types of sequences. And you're going to see this diverges and this converges. You can use the integral test to verify these. I won't really go into details with on how to prove these, but you can use the integral test. Which is basically the integral is going to be greater than the sequence because the sequence is contained in the integral. It's contained in the area under the thing, right? So you're gonna think that, okay, so you're just alternating between these series and maybe one converges, one diverges, etc., etc. So you might think there's some sort of boundary between them, but it's not really true. We can check with some other series. You're going to see that it doesn't always satisfy that, okay, now I'm taking this smaller term, it must converge. No, it's not always like that. It really depends on what you're doing. And you got to analyze it separately. And now we have the number e, which is e equals the sum n equals 0 to infinity of 1 over n factorial. And we know that it's less than 3. Why? Because we're taking we know this expression is less than e, right? And we know 1/2 plus 1/2 squared, etc., is going to eventually become 1. So 1 plus 1 plus 1 is going to be eventually 3. So this thing over here is going to be less than 3. And we're going to show how quickly it approaches to e later. So now we prove that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. The proof here, we use a binomial theorem. So to expand this over here. And we realize that every time we're just taking terms of e, multiplying them by these things over here, right? And these things are always less than 1. So this is going to end up being less than the sequence, the partial sum of e. And yeah, so that means the lim sub of Tn is going to be less than e, because that's what we're doing. We're taking the maximum limit. It's going to be less than e. Now, if we take n greater than or equal to m, we're going to observe that Tn is going to be greater than 1 plus 1 plus 1 over 2 factorial, etc., all the way to the n, to n, right? Because you're stopping at m when you're supposed to continue to get to tn. So that means it's contained in tn. So tn is greater than this thing over here. Letting n go into infinity, we obtain lim inf of tn is equal to is greater than or equal to this to the m, and we can just set m go to infinity and we get the same thing. So we're going to get these two results over here. Combining them, we get that the limit is equal to e. And notice e minus its partial sum is going to be the sum from n plus 1 to infinity of 1 to the k factorial, and this is going to be less than 1 over n factorial times 1 plus 1 over n. So instead of multiplying by n plus 2, n plus 3, etc., for the denominator, just continuing to multiply by n plus 1. And since it's going to be less than the other factorial, that means it's going to be less when you take its inverse. So it's going to be less than this thing, and we know this thing is equal to 1 over n factorial times n, and which shows how quickly it converges, because S10 approximates e with an error less than 10 to the negative 7. Okay, so I'm back. Let me just check if I'm recording again. Okay. So now we want to prove the irrationality of e. So we suppose that e equals p over q for some integers pq less greater than or equal to 1. We know sq is equal to this series over here. So that means that k factorial okay, by using this inequality over here, that's e minus Sn is less than 1 over n factorial n. We replace it with q over here, right? And we multiply by q factorial on both sides to get this expression over here. So q factorial e is equal to q factorial times p over q. So it's going to be q minus 1 factorial times p, which is an integer. And q factorial times sq is going to be q factorial plus q factorial plus q factorial over 2 factorial, and it cancels out. And we know that the terms of each factorial less than that factorial cancels out. So q factorial sq factorial is also going to be an integer. So this thing is going to be an integer. And we know it's between 0 and 1 over q, and q is greater than 1. So that means there's an integer between 0 and 1, which doesn't make any sense. It's a contradiction. So e is irrational. And now we have the root test. We set alpha equals lim sup of as n goes to infinity of nth root of an. And if alpha is less than 1, the series sum an converges absolutely. If alpha is greater than 1, the series sum an diverges. And if it's equal to 1, the test is inconclusive. And the strategy here is that you can take it to be less than some integer, less than 1, exponentiate it, take the series of that other integer. By comparison test, all the terms are going to be less than that. And since that converges because the ratio is less than 1, the other one will also converge, which is what we're doing over here. Sum Bn is a convergence geometric series, which implies that an converges. And if it's not like that, then that means that this ratio is greater than 1, which means that it diverges, which is kind of like similar to what it says over here. And if it's equal to 1, the test is inclusive because the sum of 1 over n diverges, but the nth root of 1 over n goes to 1, and the sum of 1 over n squared diverges, and the nth root of 1 over n squared goes to 1 also. And now we have the ratio test, which is the same thing, but now we're dividing the next term by the previous term. If this limit is less than 1, it's lim sub actually. There's supposed to be a supremum over here. So if its maximum limit is less than 1, then the sum an converges absolutely. If it's greater than 1, or greater than or equal to 1, then the series sum an diverges. And notice that this equals to 1 doesn't mean that the limit as an goes to infinity, the limit as n goes to infinity of an plus 1 over an is equal to 1, even though we have an equal over here. So for example, if you replace it with 1 over n over here, 1 over n squared actually, if I'm not mistaken, yeah, 1 over n squared, its limit is going to be equal to 1, right? But it converges. We know that that series converges, but its limit is going to be equal to 1. That doesn't mean that this is equal to 1 in here, because okay, when we say we're just giving a bound for this over here, what we're saying here doesn't mean that the limit as n goes to infinity of n plus 1 over an equals to 1. And actually, when the limit equals to 1, it implies nothing about the convergence of sum an. And the proof is really similar. So you're just exponentiating again because each term is less than the other. And you're going to get this, and the sum converges if beta is less than 1, right? And it diverges if it's otherwise. And this is what I was talking about here. Limit as n goes to an plus 1 equals over an equals 1, but 1 diverges, 1 converges. And now we have a few examples. We have this series 1 over 2n, 1 over 3n, and then taking the same thing, the same two terms, and then just adding another exponent. And we know the lim inf of it, lim inf of the nth root is going to be 1 over root 3. Because the smaller term between 1/2 and 1/3 is 1/3, so the limit is going to be 1 over root 3. And because we're taking the 2nth root of it, why is it root 3? Because because the 1/3 comes after every 2n terms, so you have to take the root of 2n, not just n, right? So you're going to get the limit equals to 1 over root 3, and the lim sub is equal to 1 over root 2. So this the root test works, the series converges, that's what we know. But notice the ratio test fails, because this over this is going to be 3 halves. Actually, here's supposed to be 1/2 3 halves to the end. Because one is going to be this over this, one is going to be this over this. One goes to infinity, one goes to 0, which that means the ratio test fails, but the root test works, which is an important property, because that means the root test always might work, but not the ratio test might not always work, right? And we're going to explain that why it's like that. And the same thing goes for this series over here. The nth root of an, its supremum, is going to be 1/2 and its infimum is also going to be the same thing, because we're just taking powers of 2 over here. So and you're exponentiating them, so it's going to give you less than 1. But here, lim inf is going to give you 1 over 8, because the infimum is each 2 terms repeated, right? So 1 over 8 over 1 is going to be 1 over 8, and the other one is going to be 1 over 1/2 is equal to 2. Because the ratios of each 2 terms separately is going to be equivalent for all terms of the series. So that means it fails because one is less than one, the other is greater than one. And this is due to the following theorem. Lim inf of Cn plus 1 over Cn is less than or equal to lim inf of nth root of Cn, and lim sub of nth root of Cn is less than or equal to lim sub of Cn plus 1 over Cn. And the proof is really similar to the proof of the ratio test and the root test itself, because you're just multiplying things over and over again and you're making some sort of equivalence. So Cn plus 1 over Cn is less than b, let b greater than a, right? We multiply it, and then we know for each one is less, so you can multiply it twice, 3 times, etc. to get this, and then you can, for n greater than or equal to n, you get this, which is equal to this, n minus n, you're just separating the exponents. Take the nth root. This goes to 1 as it goes to infinity, right? Because we showed that for any number you take, its nth root, when it goes to infinity, it goes to 1. It's one of the limits that we proved. So this is going to be less than or equal to beta. And we know beta is greater than alpha arbitrarily, and we get closer and closer to alpha. So that means lim sub of the nth root of Cn is less than or equal to alpha, and alpha is this thing over here, which proves this thing over here. And you can do the similar thing for lim inf and just flip the inequalities, right? And the power series is basically a series of the form like this. You've seen it in calculus. Its radius of convergence is defined as alpha equals lim sub of nth root of Cn, and r is equal to 1 over alpha. And for the proof, basically you're just going to plug in this thing. The strategy is that the nth root is going to you're basically using the ratio, the root test, and you want to find some sort of interval in which it works, and that interval is this r over here, because that's what we get in the inequality. That's the strategy. So let an equals Cn Zn, replace it, you're gonna get this, and this is just equal to alpha, which is equal to z over r. This is what we're gonna get over here. So if you want the root test to work, z over r must be less than 1, and if it diverges, z over r is greater than 1. So that's how we define the radius of convergence of the power series. For example, here the radius of convergence is 0 because this goes to infinity, because n goes to infinity, right? Here it's easier to use the ratio test to see if this converges, because and it shows that it converges for all z and c, so r is equal to infinity. Because so sometimes you can use a ratio test to find the radius of convergence because it's easier. Okay. So we have more examples. This has r equal to 1. That's basically the thing we proved earlier. This is basically the same series. Okay. This series also has r equals 1, because the nth root of 1 over n is going to give you 1 as it goes to infinity. And it fails at z equals 1 because it's going to give you the harmonic series sum 1 over n, which diverges. However, it converges for all z with absolute value of z is equal to 1, a fact that we'll prove in theorem 3.4. So we're going to explain it later. Same thing here, because nth root of 1 over n squared is going to give you 1. And here it works for n z equals 1. And we have summation by parts. Basically, you can take two sequences and take the sum of the sequences multiplied term by term, like this, And how you do it is that you know each term is the sum minus the previous sum. You replace it, you get this, and then you plug in some values for the limit points here for p equals n equals p and n equals q and n equals p minus 1, like that, and you're going to get these extra terms with followed with these. So that's, you're going to get this equality over here. Okay, and now we have the following theorem. This is the Leibniz theorem for alternating series, which you've seen in calculus. So no, my bad. This is the Leibniz theorem. I'm going to show it to you later. So let a and b be satisfying. The partial sums a n equals the sum k equals 0 to n. A k are bounded. B n is non-increasing. So basically, you have a sum and non-increasing b n such that its limit is 0. So that means the sum of a and b n converges. And you're using the same property as here, in term by term multiplication. You want to see if it converges. And the logic here is that, yeah, it does converge, because AK is bounded. Every Bn is greater is less than the previous one, right? So you can just multiply that series by a constant that is greater than the first term, and we know that converges because constant times a series converges. So that means that must also converge. But I'm going to show another proof. So with epsilons over here and with this equality over here. So choose m such that sum ak is less than or equal to m for all k, because we know that the sum ak converges. Okay. Given epsilon greater than 0, choose n such that bn is less than or equal to epsilon over 2n. And we're choosing this because it's going to cancel out nicely with these things over here. And this thing over here is going to be equal to this thing. And we know each term is going to be multiplied by an. So we're just going to bring that out with this absolute value. This is going to be less than or equal to m times this thing, and same thing for here. AQ is less than or equal to m, and AP minus 1 is also less than or equal to m. So we're going to get this. And we know that this sum over here is actually equal to BP minus BQ, because this is going to be equal to B0 minus B1 plus B1 minus B2. So everything's going to cancel out except the first and last term. So BP and BQ are going to remain. BP minus BQ which is less than BP. So this is less than, so we're just going to replace it with this, right? And MBQ and minus MBQ will go away, so you're going to be left with 2MBP. And we know Bn is less than or equal to epsilon over 2m. So that's why we chose it to be this, so that it cancels out with this 2m. So I guess a good strategy is to first mess around with this to get something like this, and then choose a number which would clean this up, right? That's a good strategy. And now we have the alternating series. Alternating series is basically when you have a decreasing sequence of numbers multiplied by an alternating -1 to the n, and the limit of all the terms go to 0. And basically what I want to do is replace it an equal to -1 to the n plus 1 and bn equal to the absolute of cn to get this series over here. Using this theorem over here, we know it converges. And now suppose some cn has radius of convergence r equals 1 and c0 is greater than or equal to c1, etc. A limit as n goes to infinity of cn equals 0. This is what I wanted to prove earlier. Then the sum cnz to the n converges at every point on the circle that's absolute value of z equals 1, except possibly at z equals 1. So the idea here is that you take an equals zn and bn equals to cn. So multiplying this series together term by term is going to give you this, and we know it's going to converge. And it converges if and only if the sequence of partial sums are bounded. And if you want to take the sequence of partial sums to be bounded, basically, this must be bounded, which is equal to this. And we know this, when it's less than 1, this is at most going to become 2, because it's going to become -1 over here. 1 minus -1 is going to give you 2. So this sequence of partial sum must be less than or equal to 2 to the 2 over 1 minus z. But notice if z equals 1 over here, if you plug in 1, it's going to be 1 minus 1. It's going to be 0. The denominator is going to be 0. So there won't be any bound. It's not going to be bounded. It won't be bounded, and it won't converge. So it's going to converge for every point except at 1. It's going to be bounded for every point except at 1, right? And absolute convergence is when, as you've seen in calculus, when each term separately has taken its absolute value. And we know that if it converges absolutely, then it must converge also, because taking the absolute value of all the terms is less than or equal to taking the absolute values of the terms separately, and we know that's less than epsilon, because its sum of absolute value of an converges. So this is less than epsilon, and we know this is less than this. And we know this is for the normal series. So the normal series is less than epsilon, so that means it converges. Okay. And we have some sequences that converge non-absolutely. For example, -1 to the n over n converges by theorem 3.43, which is the alternating series theorem. But if we take its absolute value, it's going to give us the series 1 over n, which won't converge. So that's what we call converging non-absolutely. And basically, absolutely convergent sequence behave like finite sums. They can be added term by term, multiplied term by term, and rearranged without changing the value of the sum. And rearranging the conditionally convergent sequence can change the value of the sum. And we'll show that later. We'll show what it even means to do a rearrangement. And here we show that you can add it term by term, basically. So you can just take the limit on both sides, and you can see you can add it term by term. Same thing goes for this. And now we have a really important thing, which is a Cauchy product, which is basically the diagonal product. When you have two sequences, imagine this is the first sequence, this is the second sequence. You're going to multiply all these sequences together one by one, so it's going to be some sort of rectangle for each term you're adding for your multiplication. But when you're doing the Cauchy product, you're taking the diagonal. So you're taking this, and then you're taking 1 1, and then you're taking 0 0, then 0 1 1 0, then 2 0 1 1 1 2, etc. Taking them diagonally. So a1 is when you set n equals 2 here, you're going to get a1, a2 minus 1, a0, a2, and a2, a0, right? So it's going to be some sort of diagonal sum of multiplications. And notice, since you're doing it to n and you have around 2n diagonals, it won't be the same thing as the actual product of the two sequences together. So it's not multiplying the two series together won't give you the same thing as this, unless if the series are infinite. We're going to show that right now. If the series are infinite, then of course 2n and n there won't be any difference, because 2 times infinity will give you infinity. You're going to get that their infinite sum is going to be the same thing as an infinite Cauchy product. And like I said, it's not necessarily going to be equal to the same thing as the individual products, unless if it's infinite. Yeah, okay. So an example of the product is that the product might diverge when you multiply it together, even though the series itself converge, the two series that you're multiplying converge, to show that it's different from actual multiplication. Consider this series. You're going to if you want to take the diagonal products, you're going to get like this and then like this. See, you're doing diagonals, taking 3 and 1 3 1 1 3 and then 2 2, taking 1 2 and 2 1 1 1, etc., but with square roots and inverses, right? You're going to get this series over here, and this series is equivalent to this over here, and we know that this is greater than or equal to 2 over n plus 2y, because you take this difference of squares to give you this thing over here is less than or equal to n over 2 plus 1 squared. Put it in the denominator, you're going to get n plus 2 over 2. Flip it, take the square root, you're going to get n plus 2 over 2. Flip it, you're going to get 2 over n plus 2. And that's multiplied by the n plus 1 terms you're adding. So it's going to Cn, its absolute value, is going to be greater than or equal to 2 times n plus 1 over n plus 2. And as it goes to infinity, that means limit as n goes to infinity of the infimum of Cn is greater than or equal to 2. But that means it doesn't converge, because if you want it to converge, that means it must have its sequence go to 0. Now we have Merton's theorem. Suppose an converges absolutely, sum an equals a, sum bn equals b, Cn equals the Cauchy product. And then Cn converges and Cn is equal to ab. This is basically what I said. The Cauchy product is the same thing as the infinite product of the two series. So basically you're going to prove it like this. This is the Cauchy product over here, the sum of all these over here. Because for each term you're adding all the terms less than it for n minus k. And yeah, using this that we defined here, we can use this over here, replace it with n minus k. Put it back in here, you're going to get this. And this is basically a and b plus this sum over here. We know that a and b goes to ab, because a limit as n goes to infinity of an goes to a. That's what we define over here. So if you want to show that this is equal to ab, we want to show that this goes to 0 as n goes to infinity. This sum over here. So the strategy here is you want to find some sort of thing that is equivalent to C, and show that the thing that's extra to C goes to 0. Because you're dealing with something extra and you don't like it. You want to get rid of it. Basically, this is what we want to show this. By our assumption, and this is where it's important for it to converge absolutely, we said alpha equals sum of n k equals 0 to infinity of ak. Let epsilon be greater than 0 be given. Since bn goes to 0, beta n goes to 0. Why? Because we know that each bn minus b, as it gets closer and closer to the sum, it's going to be 0. So Bn goes to 0. There exists n and n such that for all n greater than or equal to n, we have the absolute value of beta n is less than epsilon. So now we want to take this extra term and split it into the sum until n minus n, until n, and then after n, right? And so this is what we're going to get. We're splitting the sum into different absolute values. So it's going to, this is going to be a less than or equal to sign, less than or equal sign. And now here, as it goes to infinity, the sum of all these ak together will become alpha, and we know all these bn minus k's to infinity, basically they're going to be less than epsilon as defined over here. So this thing over here we defined is going to be less than or equal to epsilon a, because this part goes to 0 as n goes to infinity, because all the sum all the an's over here are going to go to there's a mistake here. There's a mistake here because this is supposed to be the sum from n minus n to n, and this is supposed to be the sum from a0 to n plus 1. Something like that. So this part will go to 0 because we're dealing with all the an from some point onwards, and it will go to 0. Because the limit as n goes to infinity of an goes to 0, because for it to converge, that's what it must do. So at the end, we're just going to be left with this epsilon alpha. So that means the lim sub of these y n's over here are going to be less than epsilon alpha. So we conclude that since it's less than epsilon and epsilon was arbitrary, this goes to 0. And since this goes to 0, that means C equals AB. And we have Abel's theorem, which is very similar. It's proved in later chapters of the book completely, but it's a very similar result if you read it. Now we have rearrangements. It's basically when we take every positive integer, a sequence of every positive integer that appears exactly once, and we set each term to be that term evaluated at that positive integer. That's going to be a rearrangement. So basically you're rearranging, you're taking this to be here, this to be here, etc., etc. Rearrangement of series. Basically imagine we have this series over here and we have this similar series over here. So basically what we're doing is in which two positive terms are always followed by one negative term. So we have 1 plus 1/3, which are the first two positive terms, and then negative 1/2. Then 1/5 and 1/7, which are the next two positive terms, minus 1/4, etc. And it's going to have, the sum is going to be of this form. And we notice all the odd numbers like this, no, all the multiples of 3 are going to be less than each other. And that means the lim sum of this is going to be greater than S3, which is equal to 5/6. But notice here, if you take these terms over here, it's going to be 5/6, and this is going to be less than 5/6. So one is greater than 5/6, the other one is less than 5/6. So they won't converge to the same thing. So that shows that rearrangements won't always converge to the same thing. And we get the following theorem, which is Riemann's theorem. which shows that if a series of real numbers converges but not absolutely, you can rearrangement to get another number. In fact, you can rearrangement to get lim inf of it to be some number alpha and lim sub of it to be any number beta. You can choose any number for their separate limits. And the proof of this is you want to take the positive terms and the negative terms. And how you do this is you take these things over here. So why are these positive terms? Because imagine this is negative, then it's going to become positive plus positive. It's going to be 2 times positive over 2 is going to be the positive. And if it's positive, it's going to remain positive and it's still going to give you the positive term. And same thing goes here, but you're subtracting to get the negative term. And if you add them, you're going to get an, and if you if you subtract them, you're going to get an, and if you add them, you're going to get the absolute value of an. And notice both of these pn's and qn's converge because sum of okay. If both were convergent, their sum would be convergent, which is not true because their sum is not convergent. And yeah, that's pretty much it for their convergence. So they diverge, basically. Now we choose P1, P2 to P3 to denote the non-negative terms of sum an. And Q1, Q2, Q3 be the absolute values of the negative terms of an in their original order. So if Q1 is the first negative term in the whole series, Q2 is a sequence, actually, Q2 is a second negative term, etc., etc. But you're taking their absolute values. And some P capital N some Q capital N are just going to be the same thing as some Pn and some Qn by their definition, except that you're just going to have a string of zeros instead of the negative terms for some Pn and a string of zeros for positive terms for the sum of Qn over here. But they're going to give you the same sum. Now, basically what you want to do, the strategy here, is that you can add infinitely many times, not infinitely many times. You can define an infinite structure of adding and then subtracting to get to the desired value, because we know both can diverge. So keeping on adding and adding and adding will give you some result, and keeping on reducing gives you another result. So that means, and you can do that to get to positive or negative infinity. So you can do that to get to any result. Basically, that's the strategy. So we now construct sequences mn, kn such that we take the first positive terms to m1 and then first negative terms to k1, subtracting them, and then etc., etc. Has partial sums that approach a desired value x and ab. So that satisfies basically the limit over here, right? Because you can take you can make it approach some value over here. You can make it approach lim infimum of Sn, which gives you alpha, and lim supremum of Sn, which gives you beta. Basically what you're doing. Sn prime, actually. Now you define sequences alpha n and beta n, which satisfy alpha n goes to A and beta n goes to B. With alpha n less than beta n and beta 1 greater than 0. And now you're just going to alternate between the inequalities, setting this greater than this less than this, and then alternating like that. So that when you alternate like this, you're going to get that this is bounded between something and something else. And that's how you get that the lim infimum is going to get you to alpha, and the lim supremum is going to get you to beta. Just like that and like that. This is possible because both sum Pn and sum Qn can diverge. Let xn and yn be the partial sums after each positive term, each positive and negative block respectively. Negative xn sum after the positive block ending in Pmn, and yn sum after the negative block ending in Qkn. Okay, so here m1 is the smallest number such that satisfies this, and k1 is the smallest numbers that satisfy this, and etc, etc. So we're taking the smallest possible values that satisfy these. So that means adding this final term over here is going to make it go greater than beta 1, because that's, by definition, this is the smallest integer for this happens. So the adding this is what going to change it to make it become greater than beta 1. And subtracting this is what going to change it for this to become less than alpha 1. So that means basically xn minus beta n is less than or equal to pmn. Why? Because basically, imagine it stops. This is the before last term, and this is where you this is beta n, right? Because it's going to be greater than beta n, right? It's going to jump over here. So when you add it. So now when you subtract xn and beta n is going to be less than the final term that you added, because the final term is that you added is a determining factor in which the final term that you added is contained, basically. This subtraction is contained in the final term you added, because okay, this is the before, let's restart. This is the before last term. This is beta n, and when you add the last term, pmn, sorry, is going to give you more than beta n, right? So xn minus beta n is this distance over here, right? This distance over here is part of this sum that you added, this final term that you added, right? So that means it's going to be contained in the last term. It's likewise for this. Since Pn goes to 0 and Qn goes to 0 and alpha n goes to A and beta n goes to B, lim sup of yn, lim yn goes to A, alpha, and lim xn goes to beta. And this is the lim inf over here, because you're subtracting for the final term, so you're making sure it's going to be at the minimum because you're subtracting, and you're going to make sure it's in the maximum, so lim sup, because you're adding the final term. Now we're getting near the end now. If sum an is a series of complex numbers which converge absolutely, then every rearrangement of sum an also converge, and all rearrangements converge to the same sum. So you can't do the same trick for absolutely convergent sequence. You can't take the rearrangement to be something else, because it's really concise, it's precise. When you have absolute convergence, the general idea is that it's really precise, and you're just adding positive terms with each other. And normally when you add positive terms with each other, not subtracting, and it gets you the same thing, then why not do it in another order? You're not subtracting for it to make another bound for it coming down and coming up, coming down. You know what I mean? Because normally in non-absolutely convergent sequences, it comes down, it comes up, etc. It's not really precise, but for absolute convergence, it's precise. And we have the proof over here. And I will explain the strategy later on. Let sum a prime n be a real image of sum a n with partial sum s n prime. Given epsilon greater than 0, there exists an integer n such that the sum ai is less than epsilon for all n is greater than n, because that's the definition of the absolute convergence. Let kn be the parameterization such that an prime equals akn. Choose p such that the indices 1 to n are all among k1, k2, kp. So you're taking a number n, any number n, you choose, and you can find a p such that when you continue with these indices, at some point, for example, you have 1, 2, 3, 4, 5. If you, for example, you have the another rearrangement, you start here, and then here, and then here, and then here. At some point, it's going to arrive at the first points, and it's going to include it. So that is all the first n terms of the original series appear within the first p terms of the rearrangement. If n is greater than p, then the difference Sn minus Sn prime, its absolute value, only involves terms from the tail sum ai equals n plus 1 to infinity of ai. Why? Because you've got rid of all the other terms from the beginning, and that means you're just dealing with terms coming after that. And you know the terms coming after that converges. And it converges absolutely. So you're going to get this. Since epsilon is arbitrary, we conclude that limit as n goes to infinity of s prime n is equal to limit of as n goes to infinity of Sn. That is, the rearranged series converges to the same sum as the original absolutely convergent series. Okay, now we have Bayer's theorem. This is actually from the exercise section. It's not really in the chapter, but I still decided to discuss about it. There's some other stuff I'd also like to talk about that I'll show later. So let X be a non-empty subset, non-empty complete metric space. Suppose n equals 1 to infinity of Gn is a sequence of open dense subsets of X. Then n equals 1 to infinity of Gn is not equal to MTZ, and in fact the intersection is dense in X. Logically, if you have an infinite sequence of dense subsets, right, then you can imagine each point is going to have some limit point around them, right, for each, because it's dense. Then, of course, for this limit point and some other limit from the other set, when you intersect them together, of course it won't give you an empty set because they're all dense inside each other, so you don't expect it to be empty. That's like the intuition of it. It's not really a proof, but I'll explain you the strategy later. The strategy basically is to take smaller and smaller subsets of the sequence of open dense subsets, and since it gets smaller and smaller and they're all inside each other, you're going to get that it's not going to be empty, because you can get smaller and smaller and it's still going to be some part of some dense subset. So let's read the proof. Let Gn be a sequence of dense open subset of a complete metric space X, and let U be in X be a non-empty open set. You want to show that U intersection n equals 1 to infinity Gn is not empty. So we're basically taking a non-empty set to show that this is not empty. So we have a point of it inside that non-empty set, to show that every dense subset, when you take its intersection, because everything is dense inside of it, then there's always going to be some dense point that's going to be part of it. So since G1 is open and dense, U intersection G1 is open and non-empty, because that's the definition of a dense set. Because if it's dense, then there's going to be some it's going to have, okay, it's either going to be a point of E or a limit point of E. So we can suppose that some G1 contains E, right? Let choose X1 is in U intersection G1, such that the closed ball X1 R1 is in U1 G1. So you're taking the intersection of this set and the dense set, and you're taking a ball inside of it for that set for that point inside of it. Now you're going to do the intersection of that ball with another dense subset, because we know it's not empty. Then take some other point and then take a smaller subset, and like that we're just netting it together, and we know it's not going to be empty. It's going to have a point because we showed later on. We showed previously that's like that. So that means X is in closed ball, X and Rn is in Gn for each n, and it follows that X is in the intersection GA the GA intersection U. Hence, Gn is dense in X because it's dense for each. It's in the. It's inside all the Gns. So since it's inside all the Gns, and it's inside the this one over here, it's going to be inside all the others, all the possible sets that you can consider for dense subsets. So that means it's going to be dense in X. Now we have the completion of a metric space. Now we call two Cauchy sequences Pn, Qn, and X equivalent if limit as n goes to infinity of Pn, Qn equals 0. Okay, so prove that this is an equivalence relation. So obviously it's reflexive because limit as n goes to infinity of distance Pn of Pn is obviously 0. It's symmetric because limit as Pn goes to Qn and Qn goes to Pn is the same thing. The distance from here to here, from here to here is the same thing. Now it's transitive because if you consider some neighborhood from this to this here to here, and some other neighborhood from this to here, you can just do the triangle inequality to show that there's also another neighborhood from here to here. So it's transitive. So it's going to be an equivalence relation. Let X star be the set of all equivalence classes so obtained. P, Q, and X star represented by sequences Pn and P and Qn and Q. We define delta PQ equals limit as n goes to infinity P and Qn. So each element of X star is all the equalities of the same Cauchy sequences. Those are going to be different elements. By exercise, okay, show that the number delta PQ is unchanged if Pn and Qn are replaced by equivalent series, and hence that delta is a distance function on X. Because why is that? Because if you change it with an equivalent series, it's going to be in the same from here to that equivalent series, and from there to the other series is going to be this the same size of neighborhoods. So that I'm just giving you the strategy to prove it. I'm not proving it myself. I'm just giving you the strategy to prove it. What do you need to think to prove it, right? And likewise, you can show it as a distance function. Prove that the resulting metric space X star is complete for each P in X. Okay. It's complete because it satisfies the Cauchy sequence, right? Because if you replace it with Pn and Pm with the same series itself, but with different n and m's, it's going to satisfy the Cauchy criterion, right? Prove that the resulting metric space X star is complete. Okay, that's what we did. For each P and X, there is a Cauchy sequence for all of whose terms are P. Let P of P be an X star be the equivalence class containing this constant sequence. So you're taking the constant sequence of all the numbers being the same thing, and we know that's going to be in that equivalence relation. and we show that the distance between P and Q is the same as distance between P and Q. Why? Because every point of the two series are constant. So at each time you're taking the neighborhoods is going to give you the distance between P and Q, because each term is P and Q's, right? In other words, the mapping phi from x to x star defined by phi p equals pp is an isometry, distance preserving map, because it preserves the distance. It is the same exact distance. Prove that phi x is dense in x star, and that phi x is equal to x star if x is complete. So phi x is dense in x star. Why? Because when you take the constant terms, then for each one of these Cauchy sequences, we know that it converges with one of these constant constant sequences, right? So we know that if we take it to be a limit point, then we can find some neighborhood that has equivalent series when you get the epsilon to get closer and closer to zero. And we know that's by definition what happens, because we prove that PP is P of P is in X star. And if X is complete, then of course that means each Cauchy sequence converges, and since it converges and each element can be represented as these things of P, then you can take it to be equal to X. And basically the general idea of this is that we call X star the completion of X. And the completion of Q, for example, is R. Why? Because the set of all X stars be the set of all equivalence classes so obtained. Because each Cauchy sequence of Q converges to some point in R. And you can take all these different points that converge to that point in R to be the same thing as in the equivalence class. And you can take all those different points of the equivalence class to represent some point in R. So you can define some isomorphism between the equivalence class and R. So the completion of Q is R. And some stuff we've forgotten to discuss in the previous chapter, I'm going to briefly discuss them here. Let X be the metric space whose points are the rational numbers Q. Okay, we saw this. A metric space X is said to be separable if it contains a countable dense subset. So if it has a subset that's dense in it, that means it has either every point of E or a limit point of E, right? And it's countable, then you can some sort of like separate it, right? Because it's dense in it, and we know that it's countable, so it's kind of like a separation of that metric space if you look at it intuitively. A collection V alpha of open subsets of X is said to be a base or basis for X if the following holds. For every X in X and over every open set G in X such that X is in G, there exists an index alpha such that V is in X is in V alpha is in G. In other words, every open set in X can be expressed as a union of some subcollection of VA. So that means you can take all these VAs and construct these open sets by doing the union of all these VAs. So that's why you call it bases, because they're the building blocks of all the open sets. And the point P in X is called the condensation point of a set E in X if every neighborhood of P contains uncountably many points of E. Why is it a condensation point? Because no matter how small neighborhoods that you take, there's going to be infinitely many points. It's like if it's condensating all inside that point, right? And from chapter 2, we have this exercise. A complex number z is said to be algebraic if there exists a0, a1 to an not 0 such that this polynomial equals 0. Now, we claim that the set of all algebraic numbers is calculable, and what we do, basically, we set for each positive number n, we can choose, we can add the coefficients of these polynomials with the degree and form an equation with it. And for each of these equations, you're basically describing every possible algebraic number, and you can count all these equations, so you can count all the algebraic numbers. That's how the proof goes. And I'd also like to point out, if you want to see a proof of why E is transcendental number, you can search it up yourself, and you can also watch a video of Michael Penn, which I really liked. It's a really good proof of it. And I really hope you liked this session and you learned something from it, and I'll see you next time. I know this was a long chapter. My name is Taha Arkian, as I said at the beginning. I hope next chapters are going to be less than this, because this was a relatively longer chapter. And yeah, I wish you all the best in your studies, and goodbye.